Assalamualaikum warahmatullahi wabarakatuh. I am Salman bin Muhammad Zainudin. This is the presentation for my final year project BMMU 4774. My study is on effect of nanofluid concentration on performance of heat exchanger. So my supervisor is TS Siti Norain binti Mohd. Okay. So my presentation content is first introduction, and there is problem statement, objective and scope, literature review, methodology, result, and discussion, conclusion. So first for the introduction. So as we know, with advancement of technology nowadays, modern computer produce more heat than ever. So the implementation is usage of microchannel heat sinks to cool the computer parts is already widely used, such as we can see at the right side, where the microchannel heatsink is used in computer cooling. So research about application of nanofluids to enhance the heat transfer performance had been studied, but the implementation is not there yet. So there is no specific concentration of nanofluid for microchannel application. So next, the nanofluid application in cooling. So nanofluid as heat transfer fluid improve thermal performance of heat exchanger. So nanoparticles have an enormous surface area which allow for increased heat transfer. The rate of heat transfer is directly proportional to the surface area through which the heat is being conducted. So this is the nanofluid application in cooling. So next, for the problem statement. So our problem statement is the current method of cooling cannot cope with heat dissipate by electronic devices, and there is no definite concentration that has been agreed which give the best performance of heat transfer. So especially for me is aluminum oxide water. So for the objective, to study the effect of nanofluid concentration on the performance of heat exchanger. Next is to carry out simulation work on nanofluid effect in the heat exchanger with different concentration. After that is to analyze best concentration for AlO3, Al2O3 water, which is aluminum oxide water nanofluid that give the best heat transfer performance in heat exchanger application. So the scope of my study is the study will be using simulation method to study the effect of nanofluid concentration on performance of heat exchanger. The study also to find the stable concentration ratio on single type of nanofluid, which is aluminum oxide water. So next is my literature review. So first, Devendran and Amritam 2016, which a review on preparation, characteristic, properties, and application of nanofluid. There is two method of preparing nanofluid, the one-step method and the two-step method. This is if we do experimental work. So next is Jasim and Ahmad to 2021 assessment of nanofluid on performance and energy environment interaction of plate type heat exchanger. Addition of nanosized titanium oxide particle to distilled water improve heat exchanger. So they show that nanofluid does improve the heat transfer. So next is Bibico et al. 2015 comparison of the heat transfer efficiency of nanofluid, which compare between three nanoparticle dioxide titanium oxide with nanoparticle which is titanium oxide, zirconium oxide, and aluminum oxide. The aluminum oxide has the most heat transfer coefficient compared to zirconium and titanium, which is why we choose aluminum oxide to study. So next is Zhu et al. experimental investigation of heat transfer for pulsating flow of GOP water nanofluid microchannel. The heat transfer performance of GOP water nanofluid improve as mass of fraction of GOPs nanofluid increases at concentration. So next is our methodology, which has the material selection first, the microchannel heatsink material selection, modeling microchannel heatsink, meshing, computational process, and data comparison. So for material selection, microchannel heatsink, we compare two material, aluminum and copper. Copper has better thermal conductivity, but aluminum has higher specific heat. For practicality, aluminum is lighter and cheaper in price, so aluminum is chosen for the heatsink material. So next, the nanofluid properties and base fluid, which is the aluminum oxide and pure water properties, and at the bottom is nanofluid properties in fraction, which is 1%, 3%, and 5%. So next, the modeling of microchannel heatsink. So the test section will be modeled using 3D modeling tools, which is SolidWorks. The test section mean the microchannel heatsink. So the dimension of microchannel heatsink is the base has 4 width and 4 length, which is 4 times 4 millimeter, and the height is 2 millimeter. The channel depth, which is 200 micrometer, and the channel width is 100 micrometer. This is one of the characteristic of microchannel heatsink, which the depth of the channel and the width of the channel must not exceed 200 micrometer and 100 micrometer. Unless if it is exceed, so it is considered as mini channel heatsink. So the number of channel we have is 11. So the microchannel heatsink then being cut to one single channel to reduce the computational time. So the meshing. So the model single microchannel heatsink is then imported to ANSYS Fluent, which the software that we use. The meshing will be generated by software for all boundary condition, but as wall, such as wall, mesh, and etc. So the meshing setting is below. So the meshing type we use is rectangular mesh. So the relevant is set to center. The relevance value is 100, and then the smoothing high. The mesh size is automatic. So the mesh size that been automate in the software is around 0.001 mesh. So the rectangular mesh is selected because the shape of the heatsink, which is simple. So if the shape have a lot of curve, so the rectangular mesh is not it's the practical. So we have to use the hexagonal mesh, which is better. We go to computational process, which is the solution algorithm and simulation parameter will be determined. Inlet velocity and temperature, such as inlet velocity and temperature, heat flux, heated base temperature, and properties of nanofluid. The ANSYS Fluent will be used in order to solve the energy equation. So the calculation is set to 500 times. So next we go to the result and discussion. So the content of result and discussion is simulation result, temperature difference analysis, heat transfer rate, and Knox-Out number. So this is our simulation result, which is the temperature contour. So as you can see, the liquid flow is laminar, and the inlet liquid temperature is uniform, which is all the nanofluid concentration have 300 Kelvin inlet temperature. So the temperature of nanofluid is increasing from the inlet to the outlet as it absorbs heat from the heatsink. So the highest temperature of the temperature contour is at 358 Kelvin, which is at the base of the heatsink. So the inlet of nanofluid 300K, then it's getting hotter to the outlet until around 317 Kelvin, which is because of the heat absorption from the microchannel heatsink. So this is our temperature control graph. These are for 0%, 1%, 3%, and 5% concentration. Okay, next, the analysis on temperature difference. So the temperature difference value increase with increasing of concentration of the aluminum oxide water nanofluid concentration. So the temperature difference in the temperature the difference in temperature difference from 0 to 1% concentration is tiny, but after 1%, which is at 3% and 5% concentration, 3 and 5% concentration, the temperature difference is increased greatly, as we can see at the graph. So the highest temperature difference is at 5% concentration, which is has 9.238 Kelvin difference. This indicate that the nanofluid does increase the heat absorption from the heatsink, where the inlet temperature is the same, but the outlet, when the concentration is higher, the temperature of the outlet will be higher, so the absorption is higher. So the heat transfer rate. So when the concentration of the nanofluid increase, it increased the heat transfer rate of the nanofluid, as we can see at the graph and at the table. So the highest heat transfer rate is at 5% concentration nanofluid, which was the rate of heat, which has the rate of heat transfer of 1.711 times 10 power of negative 3 watt. So the pure water, which is at 0% concentration of nanofluid, has the lowest rate of heat transfer, which is has 1.529 times 10 power of negative 3 watt. So we can see that the nanofluid does increase the heat transfer rate. So the Zhang et al. So found out that increase on concentration of nanofluid will increase the rate of heat transfer of nanofluid. So it is backed up with the valid research. So the Nusselt number. So the Nusselt number is 0% nanofluid has the highest inlet Nusselt number, which is at 159.591, even though it has the lowest heat transfer rate. So also the 0% also has the highest outlet Nusselt number. The 5% has the lowest Nusselt number of all the nanofluid concentration. So according to the study, this may be caused by the concentration of nanofluid increase the heat transfer through conduction that will decrease the Nusselt number. Hence the Nusselt number formula, which is Nusselt number equal to Q convection over Q conduction. So the study by Ibrahim Al-Badawi also found that the higher the concentration of the nanofluid being used, the lower the Nusselt number that he get. So for the conclusion, the different concentration of nanofluid produce different outlet temperature, which this is because the heat absorption is higher when the concentration of nanofluid increase. The rate of heat transfer also increases when the concentration was increased. This is because the higher concentration nanofluid has higher temperature difference, and specific heat. The Nusselt number is lower when the concentration is higher. So the 5% concentration has the best performance compared to the other concentration. However, so we fail to pinpoint the best concentration of aluminum oxide water nanofluid concentration because of our sample is until 5% concentration only. So the trend show that the heat transfer performance increase when the concentration of nanofluid increase. So to pinpoint the best concentration, we suggest that the next study is to higher the concentration or to compare the concentration and the performance and all other factors such as pressure drop, friction loss, and other factor. Okay. So that's all from me. Thank you.